Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 2 p.m. on Saturday, I think, in Queensland. They have a time change. I think it's this weekend, though. All right, we're broadcasting live from Thousand Oaks, California. Last week's trivia question. Do you remember? Do we have an answer?
No, but Janie's here.
Hi, Janie. So glad you could join us.
And of course, Cliff is here.
Great picture, Janie.
Yeah. And it's raining over there.
Hard to see through the raindrops to the stars.
Yeah. I was going to say, we could use some of that. Give it to us. We could use it in California, but we don't really this year.
Not this year.
All of our reservoirs are full.
So last week's trivia question was, do you remember the lyrics from the Hawkwind song? Quark, strangeness, and... I got a clip of that.
The spirit of the age. My best friends, Hawkwind!
Time and space and relativity is something that makes it very clear he was never gonna score like you and me. Didn't know about what strangeness and charm, what strangeness and charm, what strangeness and charm, what strangeness and charm.
Did you catch that?
Okay, here we've got a few that showed up during the song.
Hey, Scott.
Scott. No daylight savings time in Queensland.
Oh, is it a state thing?
Yeah.
Because Dave was talking about it.
Yeah.
Hi, Dawn. Welcome.
Dawn's here.
It is good morning for you.
Yeah.
Welcome to space.
Yeah.
It's Quark, Strangest, and Charm. Over to you.
Okay, tonight's crunchy topic, as you might have guessed, is particle physics and some recent discoveries. We'll be back in 8.3 seconds. Last July, on the 28th of 2023.
Last July.
Yeah. Well, just in case someone sees this in a year.
Oh, that's true. That's true.
2023 we're talking about. We started a conversation about particle physics. You may recall beginning with the basics. Tonight, we'll be delving into some recent discoveries involving particle physics. What's happening out there, Pam?
I want to emphasize the some, because there is so much going on in this field. I did some digging, and we could actually do every episode on this topic if we really wanted to. Let me share it here. Let me go ahead and
there we go.
Show you what I've got in mind for tonight.
And we saw this from the last time you.
Yeah. Last July 28th, we talked about this chart, and this is the standard model. I really like this one. Of course, we do have the other ones here. I just want to kind of catch you up with the basics were about really, we started with everybody kind of knows about atoms, the protons, neutrons, electrons, that kind of thing. But this kind of delves deeper into it. In fact, there are many, many, many different things that are what those atoms are comprised of, even farther in than just the protons, neutrons, electrons. Right. Okay. And so this is the standard model, but I definitely like this one a little bit better. And I talked about bubble chamber images, but I didn't show you last time. And this is an example of one. In fact, I think this is probably pretty early. See how grainy it looks? Because there are quite a few other pictures. And I found a really neat article about a bubble chamber. And I didn't know a lot of this stuff apparently this is what when they go around they spin it around the
Centrifuge.
no, it's a like
cyclotron.
Yeah, something like that. I guess they shoot it out at these things and they're separate because this is one of them and it's not part of it.
Mhm.
But they do talk about having a chamber with superheated liquid. And this, here it is, which path of an ionizing particle is made visible by a string of vapor bubbles. That's why it's called a bubble chamber. It is designed to detect charged particles through the tracks of bubbles present in a chamber consisting of liquefied gas or liquid hydrogen. It was invented by Donald Glaser in 1952. And this is, what's the website here? It's Assignment Point. So if you want to go to Assignment Point, and let's see, it says about bubble chamber. And if you want the links, we can certainly share with you. But I just wanted to kind of browse this just a little bit because they have a breakdown of what it looks like and how many pressures it's under and how it detects once it detects it, it changes the pressure so that they can expand the bubbles and it's all automatic. It flashes a picture of them. It's really fascinating. I didn't read the whole entire article, but I read enough of it to kind of get it's really fascinating. And they talk about what it's comprised of, this neon hydrogen mix. And here it is, pressure's reduced to 2 atmospheres from 5. It passes through the liquid. And sometimes they collide with these other, substances within the bubble chamber. Anyway, and that's why you get a bunch of these, like when it comes off of them, here's the particle coming in, and then it goes into like 4 different places because it hit something. Anyway, this is a fabulous article. I definitely recommend reading it. Working principle of it. Anyway, so really cool. And here's some other pictures of course, we've got that bubble chamber picture, but some of these have been colorized and they're basically Fine Art America. They've been turned into artworks, which I love that sort of thing. Anyway, and I found a whole bunch of articles on this page right here, and I really love this summary. Particle physics is the study of the elementary building blocks of matter and radiation and their interaction. The fundamental particles are summarized by the Standard Model. This includes leptons, such as the electron, the quarks that make up protons and neutrons, and gauge bosons, which mediate forces between the other particles. That just seems like a nice capsule summary. So that kind of brings us up to speed from the last episode about particle physics. All right, and of course you've got some related subjects here. I don't even know what this one means. Phenomena. Anyway.
Phenomena.
Beep, 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 beep. Yeah. All right. So one of the things I really appreciate about this is where it says open access here. And absolutely, the majority of these have an open access next to them. And they give you the date and everything. And it has changed because when I looked at this before, it said the top one was 18 September. So I guess they've added this one here. Now, you could certainly look at this from any angle that you want to. What I did was kind of look them over and go, oh, that's most interesting to me. I'm going to look at that in more detail, read it over, that kind of thing. But we could, like I said, we could do this for years. There's just so many different articles about this. And you can see some of them here. So what I did was I pulled up a few of them. Oh, this is one of them. This is actually one of them I was interested in because I'm very fascinated with this entanglement concept. And of course, dark matter. My feeling is that that's a misnomer, but we could do a whole episode on that too. So I pulled that one up. We'll see that in a second. There were just so many, and whenever I clicked on this here, I found there were 447. Of these articles. I want to go back here for a second though and show you this other part because they have news and comments, and so this one here I thought was interesting, and we'll see that in a second too, but it was different from the other ones, and I'll show you how. Anyway, so you could keep going on and really what piques your interest, what's going to sound cool to you to look at. All right, so here's that whole big list, and it just goes on. Open access. I didn't really see a difference with these ones where it doesn't say open access. I was able to look at it and read it and everything, but we did get to a point where one of these, let's see, is this? Here it is. This guy here, he wrote a response, I think, to this guy, Mark Buchanan. He wrote a response to this, and I was going along and reading it. Oh, post-particle future. That sounds interesting. However, I ran into what's commonly called a paywall. So I couldn't actually read the rest of it unless I have some kind of access through my institution, or I bought a membership of some sort, that kind of thing. So most of these articles are available to read in full, and I'll get into that one. In fact, this is probably the one I want to look at next. But some of them are, in fact, behind a paywall. All right, so again, you can just go on and on and on. What looks interesting? What do you want to know more about? What ties into something you know about? And that's part of why I looked at this one, the Entanglement Enhanced Optomechanical Sensor Array with Application to Dark Matter Searches. Well, my first thought when I read entanglement was something called the Ansible. And the Ansible was something they use in science fiction to talk about this instantaneous communication. As you can see here, in fact, when I lived in Ohio, we had something called the Cleveland Ansible, and it was basically just a little newsletter, not instantaneous, but it was very fun to share with people and get to meet the people that were involved with it and everything. So we had a lot of fun with that. So I kept reading, and I was like, oh, yeah, dark matter too. Okay, we got some good stuff going on here. And let me tell you, this gets very, very crunchy. I mean, I didn't even know what squeezed light meant, and they just go on and on and on. It's very, very technical, very detailed. So if you really like this kind of thing, absolutely take a look at any of these. And mind you, I've only really just looked at this one website, nature.com. And as it goes along, they get into more and more mathematical things. I mean, this is truly heavy-duty math. You'll see shortly. But yeah, here's the abstract, and you read along, and you kind of get the idea of what it's about. They're talking about these sensors to detect weak distributive forces for applications ranging from gravity-based subterranean imaging to dark matter searches. So lots of cool stuff in here. And then they have an introduction. These sensors are widely applicable to high-precision measurements of force, acceleration, and magnetic fields. And they have lots of what these little things would be references, which I love. I mean, I absolutely think it's very important if you're going to talk about something scientific or you need proofs for something, you want to cite your sources. Mm-hmm. So, yeah, look at this one's got tons of them. That's wild.
And don't just cite your own previous papers.
Absolutely. Yeah. I totally agree with that. It just looks like you're talking to yourself, basically. Oh, and then here we go. It tied in with this laser interferometer gravitational wave observatory. Most of the time, we see it as the LIGO, the letters that spell out LIGO.
And we've had at least one Zooniverse project.
Right,
based on LIGO data.
Yeah, and I think LIGO is just fascinating. And of course, that's when they had the two black holes that merged and it went whoop, little sound. And they got a chart. They got a nice chart from it, which basically wasn't noise. So they knew it wasn't noise. And I think that's what the project was, right? To eliminate the noise from the signal itself. All right. So there was a lot of really good stuff in here pertaining to dark matter and LIGO. And yeah, this one here is one of the most sophisticated optomechanical sensors that we've built so far. It's revealed important information about how black hole binaries merge. And that was what I was talking about, how they came together, made that sound, and we got a nice chart from it, that kind of stuff. Yep. So yeah, this whole article is talking about this way of sensors. Key advantage of the optomechanical sensors is the ability to read out the displacement of macroscopic mechanical oscillators at the thermal noise limit. We got a comment from Daniel. Thanks for joining us, Daniel.
Daniel, LIGO should sell a LIGO construction kit.
I like that. Maybe you could get a little piece of that action if you work with them and figure that out. All right, so like I said, this gets really, really crunchy. And like this is the introduction part. How far does that go on? And we haven't even look at this. We're nowhere into this hardly. There's lots more to read according to our little sidebar there. All right, so let me see what that was. Kind of cool illustration. I wanted to show you that. So they give you ways to visualize what they're talking about here. Let's see. Yeah, boy, this is just. Do you understand this stuff, Jeff?
Mhm.
Oh, good. Okay. Because there's some of it I'm just like, okay, I know this, but I don't know that. So there's a lot. There's a lot to it. Oh, beam splitting. I know that one. So what are they dealing with here? Lasers or something?
Yeah.
Because that's how that works, right?
Then they, basically they take two different paths.
Yeah, part of it goes out here and part of it goes down here.
Yeah. And then they measure an interference pattern as they come back. And that's why they call it an interferometer.
Yeah.
Because,
right.
If they're totally, if it's the exact same distance or timing for each, there'll be a very strong interference pattern. Because, the peaks will be showing up as at the peaks, the troughs will be showing up with the other troughs. But if it's taking a little bit of, any other time, and the pattern gets a little bit fuzzed out. And by how fuzzed out it is, they can measure the difference in time.
So it's not all crunchy. There's some pretty pictures like this one. And it really helps to illustrate what they're talking about. They refer to it. And this is a new one on me, this Virgo. It has something to do with LIGO. Let's see. We apply the entanglement enhanced design to a previously proposed detector based on an array of acoustic frequency optomechanical accelerometers. So, yeah. And it just goes on and on. Results in discussions. Our main result is a readout scheme for optomechanical sensor arrays that achieves global noise reduction from distributed squeezing. Yeah, this whole squeezing thing. Do you know anything about that, Jeff? I've never heard of that before. Light squeezing?
I've heard the term, but I don't.
Okay.
I don't really know what they're talking about in this case.
And here they are referring to figure 1. So maybe it's in there. Let's see if that jumps back to the figure. Oh, it puts it over here. Okay, that's cool. Oh, neat. All right, so see, I just learned that. So let's see. As sketched in figure 1, an array of M sensors jointly measures global properties of the force field. To suppress the measurement noise of the optical readout, a single mode bright squeezed beam is distributed between each sensor using a passive beam splitter array. To me, it looks like two things. So you've got the beam coming in here, and it splits out there as well as there, and then it splits again at this junction right here. So these are two beam splitters. All right. But really, it just goes on. You could spend a lot of time and really read this and understand and look at all the references. I love this kind of stuff. I could spend my life doing this, I think. Here they talk about the force sensing. For clarity, we start our discussion with a simplified model for optomechanical sensors and then proceed to the full cavity model. That's great. Starting with something simple really makes a lot of sense.
So if they're looking for particles in there, is that a cavity model search?
Yeah, I don't know. Simplified model and the bad cavity limit. Okay. Yeah, I would have to study this to really know. And like last time we talked about, there are some classes that you can take. In July, we had a whole bunch of sites that had some free classes and maybe some more pay. I don't remember. And I remember we had one of our reviewers were asking if they had to have any prerequisites. So I think the one, you just take the class. All right, here comes the heavy duty math. I don't know if you recognize any of this stuff, Jeff, but I sure don't.
Familiar with. Okay. I'm familiar with it. It's been 30 years, but I'm familiar. Oh, no. That's been more than 30 years.
More than 30 years. Okay.
Yeah, I don't want to talk about it.
To detect the motion of the oscillator, one stimulates an input light field, and they name it, which impinges like as I told you, this could get really, really in depth. And again, we're still really high in this article. We have barely scratched the surface of what this is all about. But it's great. I mean, there's lots of advances in particle physics, which I didn't know about. So I really, really enjoyed looking into this. And I think for you, if you want to delve into some things like this, absolutely do it. I think it's just so fun. It's just so fun to really dive into what you love. All right, so I won't do too much with the math there because I don't understand it, and I think it'd be really hard for most people. Yeah, look at this. It just goes on and on.
Yeah. Yeah, like I said, a lot of this is familiar to me, but it's been decades since I've played with it.
And of course, then you can come up with things like this. With the complete cavity optomechanics model, we recover the mechanical motion, induce quadrature displacement identified in equation 1. So every now and again, they do have sort of a paragraph that you can kind of understand what they're talking about.
Or at least has terms that you can
look up. I know those words. All right, so let's see. What else? Because I think there was some, quantifying performance. That's pretty good stuff.
Well, they're kind of saying, this is what we're trying to do. Then this is the testing that we're doing. Mm-hmm. This is, how we're setting up the test. Mm-hmm. And this is how we're measuring.
Mm-hmm. All right. Oh, let's look at this part. Entangled optomechanical sensor array. Squeezing the input radiation is known to increase the effective bandwidth in optomechanical sensing while leaving the peak sensitivity set by the SQL the same, thus resulting in squeezing enhanced broadband signal. This squeezing stuff, that's getting to me. I'm like, what does that mean? And of course, that's another rabbit hole you could deep dive into. All right, so let's see. Oh, okay, here we extend the results on squeezing enhanced broadband sensitivity to entanglement enhanced broadband sensitivity with an array of M mechanical sensors. I do like how they give you the figure when you click on it. I haven't seen a figure 2 yet. They keep referencing figure 1. But I think there is another one in here. So, yeah. Love, love, love this stuff. And that's the question. What is it that you love? All right, so they talk about scaling of the integrated sensitivity versus the number of mechanical sensors. Mm-hmm. Charts are always helpful. You can see the differences between these. And there is much, much more. They do have, I really like, at the bottom here, they have a conclusion. That's kind of a little bit easier to understand when you just read it. Well, that's a good chart too. LIGO versus Virgo. Yeah, let me get to the conclusion. Conclusions. See, they kind of wrap it up and you get a good idea of what they're talking about. So sometimes that's a good way to read these two, is to look at the introduction and the conclusion.
Well, they kind of go, here's what we want to do. Here's our setup.
Well, the experiment.
Here's how we're going to test it. Here's our data. Then here's our conclusions. Mm-hmm. And look at our 45 pages of footnotes
for more information. Yeah. Oh, and I just noticed here, we've probably got, we can go through the figures over here too. So this nature.com looks like a really good site. And I think they've been around for a long time, right?
Yeah. Not a bit heavy. I like it. But maths like that high that high is a bit out of my reach. Normal is good.
Yeah, I definitely, I think I mentioned last time how, some people look at this and it makes them feel stupid, but it makes me stretch myself, and I'm okay with that. I'm good with doing that. I see another comment there too.
Cliff, the easy way of reading these is look at the intro, skim the math.
Yeah.
Because there's stuff other than math that they talk about, and then look at the conclusions. And just assume that people who really know what they're talking about will have ripped this apart if they did anything wrong. So basically what they want to do and what their conclusions are what a layman needs to look at, because we're going to assume that other physicists would have ripped it apart if it if the other
Yeah,
stuff is wrong.
and even if you don't know all of it, there's plenty here to learn, and you can go as far as you want with it. If you do want to take a look at the math, you can. And of course, and like I've put over here, I pull up some other things. I've got another one over here. I'll show you in a second. But if you see something in here you want to know more about, go and find some more information and just leave it like the 2 tabs there. So yeah, go ahead with.
Yep, Janie. Fabulous Fascinating Friday Fun with Spacers. Yeah.
I like it. All right, so the conclusion here is in this work, we proposed an entangled network of optomechanical sensors for force sensing. The joint coherent processing of the sensors enable an improved scaling of integrated sensitivity versus the number of sensors. And really, seriously, the first sentence in this is probably the most important sentence.
Mhm.
And so they're kind of like putting it out there, and then they're kind of going
But
to
then they justify their
right.
Yeah, they give the conclusion, then they justify their conclusion.
Right. So if you read the first sentence and really kind of grasp what that is, I think you get a pretty good idea of the whole in this particular very, very crunchy subject. All right. So then they talk about more. And really, we're only about halfway through the page. What else is this? Oh, methods. Okay, that's cool. They detailed their experimental projections. Very good. Yeah, do you have something?
Oh, this is where they get into all of the details of stuff. Yeah.
More math.
You're probably going to see charts of data eventually.
Oh, okay. Yeah, I don't think I completely went down here. Data availability.
Oh,
Whoops.
cheater.
Oops, what happened?
Oh,
references. There's your
right.
references.
Yeah, but data availability. They didn't post their data. They were just saying
upon reasonable request.
Yeah. Well,
I like that.
Probably because there's petabytes of data.
Oh.
And, you can't really put it in an article.
Right. So I guess if you clicked on any of those numbers up there, and we could try it out, you would get to the references here. And they have a lot, obviously.
I saw number 45 at one point.
Okay, and look at this. It's almost half the page still. So let's test it out, just so we see how this page works. Because they have lots and lots and lots of articles here. Okay, how about 55?
Yeah.
Nope, it popped over here. References. Oh, that's cool. Because then you can see it right next to what you're reading. Instead of trying to go back and forth, which is very hard even with a book. So I think this is a great setup to do this. Let's see, sections, abstract introduction. So you can pop to the different parts. You can see all the figures and all the references. Awesome. All right, so that happened to be the one of the things I was interested in. And so I delved into a little bit, and it was because of this Ansible concept, as well as the dark matter thing and LIGO was in there. It's like, oh, this is so cool. So let's see. I do have one more, and this was neat because it's actually right here in our area. It's like, oh, that's cool. Let me take a look. So I did. And I guess there's a bunch of these all over the world. World's most powerful X-ray laser will film chemical reactions in unprecedented detail. So they've upgraded this laser in California. It'll produce 1 million X-ray pulses per second. That's a lot. To study ultrafast processes at the atomic level. So there's our tie-in to particle physics. All right, so here's a picture of it. The SLAC National Accelerator Laboratory in Menlo Park, California, has a 3-kilometer-long electron accelerator.
Yeah. Oh, and what they're talking about, go back up a little bit to this upgraded, 1 million X-ray pulses per second to study ultrafast processes. It's kind of like having a radar scope where, the scanning beam goes by and you see it, but things are so small and so fast that they're actually scanning 1 million times a second to see the motion. So that's
hard to imagine 1 million times a second of X-ray pulses. It's mind expanding. All right, so then they go into how it's been upgraded to become the most powerful in the world. Produced its first beams on 12 September. That was just recently. And Menlo Park. I know I've heard of it, but I'm not sure where that is. Do you know where that is, Jeff?
That's Northern California.
Oh, Northern California. Okay. So maybe not in our area, but certainly in our state.
Yeah.
produce 1 million X-ray pulses per second when running at full capacity. And again, there's a bunch of these all over, but I guess this is the fastest one or something. A $1.1 billion upgrade to the LINAC coherent light source housed at the SLAC National Accelerator Laboratory. Yeah, I saw it.
Slot machine eyes. Wow, so fast.
Yes, very fast. All right, so I don't think I'll go as in depth on this because you can read this. I mean, this is nature.com again. But you know, what is it that you're interested? Super fast science. I like that. They started in 2009, became the first instrument in the world to combine the atom probing capabilities of high energy hard X-rays with the speed of a laser. Yeah, what's Daniel got to say? I see it.
1 million hertz frequency has a wavelength of 300 meters.
Okay, all right.
Or 1 megahertz, yeah, frequency. Yeah.
What's Cliff got?
Got to be quick with the switch per million a second.
Right? This is hard to imagine. I mean, even talking about some other kinds of numbers. I mean, I know a second is a length of time, but it doesn't seem very long.
Yeah, I'm surprised they could get away with that.
Why is that?
This is California. Automatic laser gun. You're not allowed to do automatic weapons. It has to be single burst per pull of the trigger.
Right, got it. Okay. All right, so let's just read the headlines. Super fast science. Oh, it's a cool picture. The undular system that creates LCLS3's X-rays has been upgraded over the past decade. Yeah, very cool stuff. Place pop kite. Definitely take a look at some of this stuff, especially if it grabs your attention, if you like the topic. Leapfrogging the competition. Yep, this was cool. Because there's a number of these all over the world, which I didn't really know. Some nice pictures. Oh, I think this is a different article, though. That's a different article.
Still a nice picture.
Yeah, it's a cool picture. All right, what else is in here? References. So this one isn't quite as long as the other one. So you've got a variety here.
Well, it's not like they were trying to prove anything. They're just bragging.
It's an announcement.
They're just bragging about their big gun.
Okay.
Mine's bigger than yours.
So here's that guy's his response, I guess. And and this was interesting to me because I'd never heard of this pentaquark. Nothing strange about this pentaquark strangeness. The Large Hadron Collider yields a 5-quark particle that includes a strange quark as predicted by theory. And I'm looking forward to reading this, and then you realize you cannot. It's got a paywall too. So again, there's some of these, and it seemed like quite a lot that were available to read, and some of them that were not. So what I did was I just went and copied that term, pentaquark, and I went over and looked for it. And voila, I get some information, even though I can't read the article, because I never heard of this before.
Yeah, because most protons and neutrons have 3 quarks.
Yes, right. So this one is something that we have actually created, and it consists of 4 quarks and 1 antiquark that are bound together. They are not known to occur naturally or exist outside of experiments specifically carried out to create them. I think it was, yeah, go ahead.
And this article, right, just in the next paragraph, actually explains what a baryon is.
Yep.
So that's cool.
Yeah, there's a lot of good stuff in here. Even though I couldn't read the article over there, I did a search for the term, and I've learned a whole lot more about it.
Of course, baryon number of plus 1/3. Plus 1/3 of what? But that's probably if you look up baryon number, yeah.
In particle physics, the baryon number is a strictly conserved additive quantum number of a system. And it goes on. It's defined as, and we don't get the rest until you go there. Mm-hmm. So you could absolutely look at every single one of these clickable links. They're in blue. They show up with an underline when you hover over them, and they give you a little description. So yeah, I thought this was just so fun to really play around. Just dive in, figure out what you could. Was there something else I wanted to share with you here? So they talk about, again, quark is a type of elementary particle, has mass, electric charge, and color charge. Oh, this was kind of fun. I was like, oh, interesting, right? Color charge, flavors. And I think that's with that standard, the standard model, these.
Mhm.
All right, so it all kind of tied back into each other. They talk about the structure. Oh, I really like this part too. A wide variety of pentaquarks are possible with different quark combinations producing different particles. And they have this identification. So it's like the letters and then a letter with a line over it. To identify which quarks compose a given pentaquark, physicists use the notation, in this case, Q, 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 and there's another one, fourth. And then would that be a prime Q? Would that, with a,
Well, let's see.
okay, here it is. We're Q and Q with the top bit, respectively refer to any of the 6 flavors of quarks and antiquarks. There it is, antiquark. Must be the antiquark, right?
Mhm.
So we have up, down, strange, charm, bottom, and top. And so here you go, all these different ones. And I'm reading along, and I was like, as they mentioned one, I was like, oh, I know, here it is, up, up, down, charm, anti-charm. So you can read it. It's a nice, it's great. They've got all kinds of different designations for these. And here's a good diagram. See, a penta for 5, right? Pentaquark possibly discovered in July 2015, showing the flavors of each quark and one possible color configuration. Yeah, so. And you can do this too. Absolutely. You find something you like, have at it, have fun. There's a lot of good stuff in here. You could definitely get lost for a while. Oh, and this made me think of something. So stay tuned for that one, the Feynman diagram. Yeah, do you have something?
Well, yeah. Did you see anywhere in here whether the pentaquarks are stable?
Oh, you know what? I did not catch a wind of that, but it makes sense that it might not be.
Which is why we don't see them in nature.
Right, because a lot of things that humans create don't last very long. And so, again, they're not that stable.
Well, it's because it takes a high energy to do it. And they've got so much energy that any other state is a lower potential energy state. So
yeah, and things naturally want to come to the lowest state that they can.
And even if they've got it on a equilibrium where it's not going to change from that state, all it takes is something to jostle it. It's kind of like being at the peak of a mountain. If you're standing on the very peak, all it takes is a nudge, and you fall down, one side or the other.
Mm-hmm. Okay, I like this part. 2 applications. The discovery of pentaquarks will allow physicists to study the strong force in greater detail and aid understanding of quantum chromodynamics, which is a new term to me too. So, let's hover over this, see what we get. In theoretical physics, quantum chromodynamics, QCD, is the theory of strong interaction between quarks mediated by gluons. Quarks are fundamental particles that make up composite hadrons, such as the proton, neutron, and pion. QCD is a type of quantum field theory, and then it goes on. All right, so in addition, current theory suggests that some very large stars produce pentaquarks as they collapse. And that's a nice tie-in too. The study of pentaquarks might help shed light on the physics of neutron stars. How cool is that? All right, so let's see what else here. Oh, I wanted to point out that when I was looking at the pages on Nature, I saw something. I meant to mention at the beginning, view all journals. So what I did was I looked at that, and you can get to them alphabetically or just look at them all in a list. There's some quick links. I think this is a wonderful site. I think you're going to have a lot of fun if you want to check this out. So yeah, again, we could go on for a very, very long time regarding particle physics. And I think it'd be great.
Yeah.
So that's what I got for you tonight. Again, just keep going and going and going. But I don't want to take all your time.
I'll do that.
Okay.
Okay.
Yeah, you could definitely follow up with another
Well, in fact, next week I will be. It's just something that I saw just recently, so I just figured, oh, let's
Yeah,
get on this
he
one.
was telling me about it for my show, and I was like, no, I want to talk about it. Okay.
Yeah. So that's next week.
Yep.
Because there's more there than just like a throwaway line during this show. So some stellar events this week, September 22nd through September 29th. On September 22nd is first quarter moon and the moon runs low.
Oh, that's tonight.
Yeah. Also, Mercury is at its greatest western elongation. Look east before sunrise. Mercury is 18 degrees above the horizon.
That was this morning. And
oh, yeah.
It was too cloudy here to see that. But of course, it's
Yeah.
still going to be, it comes up and then it starts going down, but it's not.
Yeah. Well, it was actually pretty clear straight up, but, cloudy on the horizon, which that's where this was. So, okay. September 23rd is a autumnal equinox.
It's the equinox.
Yeah. September 24th is Yom Kippur. Kippur begins at sundown, and Pluto and the moon are in conjunction. September 26th, Saturn and the moon are in conjunction. A much better show than Pluto and the moon being in conjunction.
At least naked eye. Yeah.
September 27th, moon is at perigee. September 28th.
Closest to us.
Yep. Neptune and the moon are in conjunction. September 29th, Friday night show. Another crunchy topic, and I'll tell you more shortly.
Yeah.
Second tease on that. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. Also on September 29th, full harvest moon, and the moon is on the equator.
Oh, now see if
it's going to be much easier to harvest now since it's on the equator.
And if it had been on the 27th when it was at perigee, it would have been a supermoon too. So that's the current terminology for it. All right, some other events and activities. I wanted to tell. Oops, let me set it up and then you can share. I wanted to tell you about this thing, and everyone can participate because it's online. NASA's OSIRIS-REx asteroid sample return mission. All right, so this is happening, gosh, not even 2 days from now. It's like 36 hours or so. Yeah, and this is going to be broadcast, and you are invited to participate. Let's see if I can read the main stuff here. NASA is inviting the public to take part in virtual activities ahead of the OSIRIS-REx's origin spectral they spell it out. Origin spectral interpretation and resource identification and security regolith explore the asteroid sample return mission. This mission will help scientists investigate how planets formed and how life began, as well as improve our understanding of asteroids that could impact Earth. Let me go ahead and share this page here, because it takes you over to
Cliff. A little bit ago.
Oh yeah.
Clara's mud.
Sorry, Cliffy.
Chris of the new scope. Yeah.
Oh yeah. So that's the link to that, and when you're in there, right down here it says members of the public can register to attend the sample return virtually. As a virtual guest, you will have access to curated resources and mission-specific information delivered straight to your inbox. I believe I registered for this a couple of days ago. Live coverage will begin at 10 a.m. Eastern Time on September 24th at 7 a.m. for us on NASA television and the agency's website as well.
Oh, that's Sunday.
Yeah, it's Sunday morning for us, bright and early, 7 a.m. here, 10 a.m. Eastern Time. And when you click on the register, you get over to this Eventbrite page. It's got a neat patch. And you just sign up, reserve a spot. You can. I don't see any point in saving more than one. It is a free event, and then you'll get emails about it. And
the reason to say more than one?
Yeah.
Because if there's like 3 people in your household that are going to be seeing it, then that'll give them the numbers of people.
Yeah. Join NASA to participate online for the OSIRIS-REx asteroid sample return mission. And they give the date and time. It's online. It'll be about an hour long. It'll provide communications about returns, scheduled changes, information about highlighted mission activities, and access to curated mission resources. Be our virtual guest for OSIRIS-REx asteroid sample return mission. And it sounds like this is not the exact date it's going to come back, but this is the leading up to it, I think is what. Anyway, but you can read this. I can go ahead. Well, no, you've got the link. You got the link to this page. If you want to register, go ahead and click on this one here where it says register. That'll take you to this, and you too can participate in this event. Nice thing about Eventbrite too is at the bottom here they give you that's the one I signed up for. NASA's Psyche mission. Okay, I better register. I gotta reserve a spot, but it has a timer, so I'll do it later. All right, back to us.
I was going to be procrastinator, but I decided to put it off.
Okay. And remember, if you're in Australia, you can name the rover. That is still going on till October 20th. And then they're going to give a short list of 4 names that can also be voted on, I guess. And the winner will be announced on December 6th of 2023. That chosen name will be engraved on the Australian-made rover that will head to the moon by as early as 2026. Did I see another? Nope, that was okay. And here we are.
Okay, if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, September 29th. I'm going to talk about dark photons.
That's the article he sent me.
Yeah. And it's just, dark.
They decided to take it back.
Dark matter.
Indian giver.
Yeah. Dark matter, dark photons.
Good stuff. Good stuff.
And tonight's trivia question: what are darkons?
Maybe somebody out there remembers that, Cliff.
Yeah. It's a much older concept than dark photons.
Mm-hmm.
Join us again next week, and we'll answer it and see if you got it right.
All right. So let's do a shout out. Cliff, Daniel, Janie Becker,
Dawn.
And
And
I know Scott was in here. There's
yep.
Scott.
Yep. I think
Thanks so much. Yeah, that was it. Thank you so much for joining us. We really appreciate you being here with us and learning. And we always love it. And you contribute so much. Much. This would be much lesser if you weren't part of it.
Yep.
Thanks again, folks. Have a great week.
Good night.
See you next Friday.
Mhm.
Bye.